Okay, good afternoon, everyone. I'm Biso Gemire, and I'm a bioinformatician at, can you hear at the back? I'm a bioinformatician, and I'm doing half-time in single-cell genomics. And now I'll talk about removal of confounding factors in this part of the day. So let's see, what are the confounding factors? So in our data, there might be some third variable, third factor that is influencing our outcome together with exposure. So let's say there is alcoholism has true effect on oral cancer. That is what we want to study. But there might be some other variable doing something to the outcome. Let's say people smoking. The smoke might have some effect in the oral cancer apart from alcoholism. So that smoking is a third variable that will affect the oral cancer. So it is a confounding factor. And it has also effect on the exposure. So people who smoke, they are more likely to drink. So we are studying drinking and its effect in oral cancer. But those people who smoke, they have influence on both outcome and the exposure. So that is called confounding factor. And it will bias our result. So that we really need to take care of those kind of variable that has hidden effect in our study. So here is the same thing. So we have exposure, alcohol consumption, and the outcome, oral cancer. And there is smoking that distorts the relationship between exposure and the outcome. So we have to adjust the effect coming from those confounding variables. So what are the approaches to deal with those variables? So in the experimental design phase, we can take care of those variables. For example, randomization. So we try to randomize our experimental subjects and put into smoking and non-smoking group. But the problem with this is it has very limited applicability. Like we have people drinking and the outcome is oral cancer, and we cannot ask our subjects to smoke. So that is very unethical. So it has very limited applicability. So we cannot use that much this randomness. And the restriction, another approach, in restriction we can take only those subjects, those experimental units that do not smoke. So we do not take into account that factor. That can eliminate the confounding factor effect, but the problem is we cannot generalize our experiment to the population. So there are people smoking and non-smoking. Our study cannot be generalized. So it also has some limitation. And another approach is matching. In the matching, what we do is we try to find a control. Let's say there is one experimental unit, one person who smokes, and we try to find another person very similar to that one in other aspects, but doesn't smoke. So we try to match. And if you are doing a lot of experimental design, you might know a lot better than I do about these things. And we can also adjust confounding factor in the data analysis step, and there are different approaches. Here we discuss about multiple linear regression. And you can do that by logistic regression, analysis of covariance, and there are tons of other new methods. How many of you are familiar with linear regression? Okay, quite a few. So I'll try to give some overview about linear regression. So let's say we have two variables, x and y. Y could be, for example, expression of a gene, and x could be some other variable. And we try to make a scatter plot, and we can see there is some very some kind of relationship between x and y, some kind of, when x grows, y also grows. And if we can put some line there, it can give some kind of idea that those two variables are linearly related. Like, for example, this. So the line can fit with the data points there. So that would be our linear model. And that model is described by this equation. So what is y? Y is our dependent variable, and x is our independent variable, and b naught is, when we extend that line, is the point where it touches the y-axis, so it's intersect. And b1, so b1 is the distance from here to here in such a way that this distance is 1 unit. So what does it tell? For every unit change in x, what will be the changes in y? So it tells the effect of x on y. So in other words, this is a constant of the model, this is the coefficient of the model. And there is another term called residual. So residual is the distance between each point and the regression line. And how do we solve B1 and B0? So B1 is given by R, Pearson correlation coefficient, and the standard deviation of y divided by standard deviation of x. And similarly, B0 is mean of y minus B1 mean of x. Okay, so next we go to the concept of R squared. What is R squared? It's a coefficient of determination. So R squared is given by variance explained by the model. So how much the model explains the variation and the total variation. So here we are looking the variation on y. So first we calculate the variance explained by the model. Here I haven't calculated the variance but the variation, so it's not divided by n by 1. So here I calculate variation in y. So how do we calculate variation in y? We have a mean of all the points. For example, this is the mean line. And then, so I had taken 3 points, this one, this one, this one in here. So y minus y mean here, and we square it. And we do the same for all the points. So it gives the variation in y. And next, how we calculate the total, sorry, this is the total variation, and how we calculate the variation explained by the model. So the variance explained by the model is, we have the regression line, and when we give, for example, this point to the model to predict the output, I forgot to mention this thing here. So once you feed this model, you can predict for new value of x. So if you give new value here, which is not here, then we draw a line here and here. So that will be our predicted value of y. And what we can do, we can predict the same point we have here, right? So if we predict this point and extend the line from here to here, the predicted value of y will be here, but the actual value of y is here. Did you get my point? So there is some difference in the actual value and the predicted value. That is because of the error in the model. The model is not perfect. So if all the lines fit in the line, they are overlapped in the line, then we get perfect model and we get perfect prediction. But that doesn't work in real life. Everything doesn't work perfectly. So there is some error in the model. So this is the point predicted by the line. So now here we try to calculate what is the variation explained by the line, explained by the model. So how we do? We have this predicted y for this point, and we subtract that from our mean, and then we square, and we add up all, or for all points. That is how we calculate the variation explained by the model. And we put that over here, we get r square. So what is the significance of r square? So when we do linear regression, we try to find out what is the effect of x in y. So because of the linear relationship between these two variables, how much variation in y explained by the variable x? So that is what we're looking. Let's say all these lines, they overlap here, overlap with the line. What happens? This term will be equal, right? Then we have 1, which is 100%. So 100% of the variation in y is explained by x. So that is a perfect fit. Because this comes very handy when we are looking into confounding variable and how it influences our gene expression. And we can see that in our exercises later on. So I try to come up with some very simple example. Here we have cells, and I have put only 2 genes and their expression. This is totally simulated. These are not real count. And here are the hours, so different time point where the expression have been measured. And here I try to look into the effect of hours with the expression of this gene. What I do, I plot this and hours in x-axis, and this count here. So you can see a linear relationship here. We can fit a line. So the equation of line is given by this, y equals to b0 plus b1 x. And when you use R or any statistical package, when you give the data, it gives you these values. So what these values tell, like for example, this coefficient of x, so every 1 unit increase in hours will, every 1 unit increase in hours, there will be 3.93 increase in the expression. So that is what it tells. So we can also simplify that. So expression of BRCA1 is 22.42, which is the intercept given by the model. And this is the effect and the hours. And if we put these hours here, so it will give you some value for this one. That should be very close to this one. It won't be exactly that one because the model has some error, but it will have. And I haven't, you can add that error here, which I didn't add here. So that is how it works. Okay, let's say we have more than one variable, hours, and let's say those cells are from each of different A's, and the A's is in month here. So we have 2 confounding variables playing now. So we want to have effect on them. We have to check effect of those variables in the expression of this gene. So we can generalize our previous model. So our previous was simple linear regression. It had one independent variable and one dependent variable. So one independent variable had some role in another dependent variable. But here we have two independent variables. And we have one dependent variable, which is the expression of that gene. And we can extend that model by just adding the coefficient and that variable to the model. So previously we had only this one. Now we add this. And if I again make a scatter plot of the expression of this and to this variable separately, we can see some kind of linear relationship over here. Okay, so this is multiple linear regression when we have more than two independent variables. Here, what I did, I included only hours in the model. So this is our first model, the simple linear regression. So there was effect of X is 3.39. But when I include both hours and A's in the model, the actual effect of X is 2.64. It got decreased. So we can say that there is some other variable that had influenced X in such a way that the effect was higher here. So we have to take out that effect from our data. How we do that? We just include that in our multiple regression model, and the model take care of that. So effect of X2 is regressed out by just including that variable in the model. And it another thing. So after doing multiple linear regression, it gives residuals. I don't know if you remember residuals, like I showed you here. So the residual is the predicted value and the actual value, the difference. And when multiple linear regression gives you the residual, those residuals are the corrected value. So we use that value. And that is what exactly scRNA has done. In scRNA, what we do is we use the scale data function to do the correction of those confounding variables. And we put the scRNA object and the variables to regress. And doing that, the scale data calls regression out resid. So that gives you the residuals. And the residuals have, the residual, they do not have effect of confounding factors. And we can use that in our data, and the bias is removed. And those return residuals are lattice scaled. One thing we need to remember is using this function, and when we give what variable to regress out, we have to have that in our scRNA metadata column. So if you do scRNA object at the red metadata, then you can see all the columns in the metadata. Probably from the earlier exercises, you have there some kind of correction in mitochondria gene. Is there, Osa? Have you used some correction for mitochondrial count? Yes. Yeah. Yeah. So what you do is you put that variable here in the metadata column, and you just mention to the scRNA function, and it corrects the effect coming from that confounding factor. And there are other tools that can do the same thing. So linear regression is kind of very basic kind of thing. And there is scLVM, scRemover, and scTransform. So scTransform is also a part of scRNA. So scTransform is also a normalization method, and in the same function you can you can do this confounding factor correction. And CC remover, they said that it outperforms scLVM slightly. I haven't tried myself, they have R package. And scLVM, it is mainly designed for cell cycle variation removal, but they said that it also corrects other confounding variables. But in their GitHub, they said that for this, they don't have manual yet, and the program itself in beta pre-release, so probably I'll still wait once there comes a stable release, and then I try to use it. Yeah, that is my part. Thank you very much. Do you have any questions?